Trigonometry can feel intimidating, but it's really just about comparing sides of a right triangle. Ratios, not rocket science. Let's walk through this step by step. In a right triangle, we always have three sides. The hypotenuse, the longest side, always opposite the right angle. The opposite side is across from the angle we're looking at. The adjacent side is right next to the angle we're looking at. Now that we know how to identify opposite, adjacent, and hypotenuse, the next step is learning how to use them in formulas. This is where the three main trig functions come in. To remember which side goes with which function, we use a simple memory trick, SOH-CAH-TOA. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. If you can say SOH-CAH-TOA, you can solve right triangle problems. Before we practice with SOH-CAH-TOA, let's make sure we know how to use the calculator. First, check your calculator's mode. Look at the screen. If it says RAD, that means radians. For now, we want DEG, which stands for degrees. Switch to degree mode, or your answers will come out wrong. Here's a quick demo. Take the angle 40 degrees, press tan, type 40, and hit equals. You'll see about 0.8391. That's the ratio of opposite over adjacent for a 40-degree angle. And don't worry, if you don't have a physical calculator handy, there are free scientific calculators online you can practice with. Just make sure they're set to degrees. So let's see these in action. You're given an angle of 30 degrees. You're told the hypotenuse is 10, and the goal is to find the opposite side. Which one of our trig functions contains opposite and hypotenuse? The sine function, SOH. This is the function we will work with. Line up your problem algebraically. Sine of 30 degrees equals opposite over hypotenuse. Now calculate the sine of 30 degrees and you get 0.05. So we now have 0.05 equals opposite over, what is our hypotenuse? 10, right. Our next step is to isolate the unknown, which is the opposite. And if we want to isolate it, we have to use our algebra to remove the 10. And to move it, we have to perform the opposite operation. Because the opposite side is being divided by 10, we must multiply by 10. And whenever we do something to one side, we have to do the same thing to the other. Meaning we're going to need to multiply the left side by 10 as well. This leaves us with 10 times 0.05 equals our unknown. So multiply your 10 times 0.05 and you get 5. There you have it. This is the length of our opposite side. Now let's try the cosine function. We're given an angle of 60 degrees and we're told the hypotenuse is 20. The goal is to find the adjacent side. Which trig function connects adjacent and hypotenuse? That's right, cosine. Remember, CAH, C-A-H, cosine equals adjacent over hypotenuse. So we set it up. Cosine 60 degrees equals adjacent divided by hypotenuse. Next, calculate cosine of 60 degrees on your calculator. Cosine 60 equals 0.5. So now we have 0.5 equals adjacent divided by 20. Our unknown is the adjacent side. Since it's being divided by 20, we do the opposite operation and multiply both sides by 20. That leaves us with adjacent equal 20 times 0.5. And multiplying gives us our unknown is 10. The adjacent side has a length of 10. There you go. Now let's look at the tangent function. We're given an angle of 45 degrees, and we're told the adjacent side is 8. The goal is to find the opposite side. Which trig function connects opposite and adjacent? That's right, tangent. Remember, TOA, tangent equals opposite over adjacent. So we set it up. Tangent 45 degrees equals opposite divided by 8. Next, calculate tangent of 45 degrees on your calculator. Tan 45 equals 1. So now we have 1 equals opposite divided by 8. To isolate the opposite, multiply both sides by 8. That leaves us with opposite equals 8 times 1. So the opposite side is 8. There you have it. Tangent shows the ratio between the opposite and adjacent sides. Up to this point, we've worked with right triangles, but in construction, not every triangle has a 90-degree angle. Roof trusses, sloped supports, and irregular lots often form oblique triangles, triangles without a right triangle. To solve these, we use the law of sines and the law of cosines. These tools let us find missing sides and angles just like SOH-CAH-TOA, but for any triangle. The law of sines says A over sine A equals B over sine B equals C over sine C. That means the length of a side divided by the sine of its opposite angle is the same for all three sides of a triangle. Example, a roof truss forms a triangle with one angle of 30 degrees, and the side opposite it measures 10 feet. Another angle is 105 degrees, and we want to find the side opposite it. Okay, so let's set everything up. The law of sines says A over sine A equals B over sine B equals C over sine C. When we plug in what we have A is 10, 10 over the sine of 10, which is 30, equals our unknown over the sine of 105. Breaking that down, we calculate the sine of 30, that comes out to 0.5. So now we have 10 over 0.5 equals our unknown over, calculate sine of 105, and you get 0.96. Next, we take 10 and divide by 0.5, we get 20 equals our unknown over 0.96. Now we need to isolate our unknown, and because x is being divided by 0.96, we need to perform the opposite operation in order to move it to the other side. So we multiply by 0.96, and remember, whatever we do to one side, we must do to the other. So we must multiply 0.96 to the left side of the equation as well. That gives us 0.96 times 20 equals, you're left with x by itself. Because when you have a 0.96 in the denominator and the numerator being multiplied together, they cancel out. Now 0.96 times 20 gives you 19.2. There you have it. The length of your unknown is 19.2. Sometimes we don't know enough angles to use the law of sines, and that's when the law of cosines comes in. Think of it as the Pythagorean theorem for any triangle. The formula is c squared equals a squared plus b squared minus 2ab cosine c. For example, a surveyor measures a triangular lot. Two sides are 80 feet and 65 feet, with an included angle of 120 degrees. We want to find the third side. Okay, let's work this out. Our formula is c squared equals a squared plus b squared minus 2ab cosine c. If you see your diagram below, you'll see that a is 80, B is 65. Our cosine C, our angle, is 120 degrees. Let's plug those numbers into our formula. C squared equals, A squared is 80 squared. That's 6,400. Plus B squared is 65 squared. That's 4,225. Minus 2 times 80 times 65. Calculate your cosine C and you get a negative 0.5. Let's start working these out step by step. C squared equals 6,400 plus 4,225 gives you 10,625. Minus, let's multiply the rest of them together and be careful with our signs. 2 times 80 times 65 times a negative 0.5 gives us negative 5,200. We're in the final stretch. C squared equals, we have 10,625. Now you have two negatives being multiplied to each other there. That makes a positive 5,200. Now we have a square next to our unknown. And if you recall, if we follow our algebra, in order to eliminate a square, we have to do the opposite operation, and that's a square root. If you need an algebra refresher, go to Field to Compliance Math Bites. We take the square root of both sides, and 10,625 plus 5,200 gave us 15,825. The square root of that is 126, and so our answer is 126 feet. There you have it. Now let's turn to circles, an important shape in both math and the construction field. In construction, circles show up more often than you might think. Manholes, tanks, round foundations, pipe cross-sections all require us to know either the circumference, the distance around the circle, or the area, which is the space inside the circle. The formula for circumference is C equals 2 pi r, where r is the radius. Think of circumference as the length of material you need to wrap around a circular footing form at a substation. For example, the crew is forming a round concrete footing. Radius measured from the center to the form wall is 4 foot. C equal 2 pi r. 2 pi r, if r is 4 foot, is roughly 25.1 foot. That's how many feet of form board or rebar or tape you'll need to go all the way around once. With just the radius, we can solve for both circumference and area, two measures that come up again and again in the real-world construction. That formula is A equals pi r squared. That means we take the radius, multiply it by itself, then multiply by pi. For example, if the radius of our circular footing form is 4 feet, we calculate the area, pi times 4 squared equals pi times 16, which is roughly 50.3 square feet. So what does that mean on the job site? Think of the area as a surface inside the form. If crews are pouring concrete, this number tells us how many square feet of coverage we'll fill. In other words, the radius alone gives us everything we need to know about both the distance around and the surface inside a circular foundation. Now let's look at cubes, another shape you'll find often in the field. In construction, cubes show up in things like concrete test samples, structural blocks, or even storage boxes. To fully understand a cube, we need to know two main measurements: the volume, which is the space inside the cube, and the surface area, the total area of all its outer faces. The formula for the volume of a cube is V equals S cubed, where S is the length of the side. Think of volume as how much material can fit inside. For example, a crew pours a test cube with each side measuring 2 feet. Volume equals 2 cubed, which is 8 cubic feet. That's how much concrete fills the mold. The formula for surface area of a cube is SA equals 6 times S squared, because a cube has 6 equal square faces. For example, using that same 2-foot cube, SA equals 6 times 2 squared, which is 6 times 4, which is 24 square feet. That's the total surface of all 6 sides. So what does this mean on the job site? The volume tells us how much material goes inside the cube, while the surface area tells us how much covering, coating, or formwork we'd need on the outside. In other words, knowing just the side length gives us everything we need to calculate both the inside space and the outside surface of a cube. Moving on, we'll cover cylinders, another common shape in the field. In construction, cylinders show up all the time. Pipes, tanks, poles, and even concrete columns. To fully understand a cylinder, we need to know two main measurements: the volume, which is the space inside the cylinder, and the surface area, the total outer area, including top, bottom, and curved sides. The formula for the volume of a right circular cylinder is V equals pi r squared height, where r is the radius of the base and h is the height. For example, a concrete column has a radius of 3 foot and a height of 10 feet. Your volume is pi times your radius is 3, so 3 squared, times 10, which is your height. Pi times 9 times 10 equals approximately 282.7 cubic feet. How much concrete would be needed to fill the column mold? Now, the formula for surface area of a right circular cylinder is SA equals 2 pi r height plus 2 pi r squared. The 2 pi r height is the lateral surface area, the curved side. The 2 pi r squared is the two circular ends, the top and the bottom. For example, using the same column with the radius of 3 foot and the height of 10 foot, surface area would be 2 pi times 3 times 10 plus 2 pi times 3 squared. That gives you 60 pi plus 18 pi, which comes out to roughly 78 pi and 245 square feet. That's the total surface of formwork around the column, including the top and bottom circles. On the job site, the volume tells us how much material, like concrete or any liquid, the cylinder can hold. The surface area tells us how much formwork, coating, or covering we'll need for the outside. In other words, just knowing the radius and height gives us everything we need to calculate both the inside space and the outside surface of a cylinder. That wraps up our quick look at trigonometry for the OHST exam prep. Remember, you don't need to master all the advanced identities. Just be comfortable using sine, cosine, and tangent for practical workplace problems like ladder safety, slopes, and forces at an angle. Next, we're moving into statistics, where we'll cover averages, variation, probability, and how they apply to safety data in the field. Let's jump in.